Welcome to Cute Widgets and More. Would you love to be able to read this code? Yeah, I'm waiting. Just read. Okay, time's up. Did you understand everything? If not, stay tuned for this 4-episode long mini-series on template metaprogramming. Okay, let's not go into much detail about this code. It's what we'll be talking about the next 4 episodes. The background of all of this was that I had a container library or an algorithm library that I wanted to show you, but it wasn't GPL. So I thought, how hard can it be to recreate it without getting too much inspired by the original one? And that part was super easy for me, the not getting inspired, because I understood zip from the original one. But I learned enough metaprogramming, and I had the fortune of having a good coworker guide me through the process, and this is the result. And I'll walk you through every single step that you need to know to recreate it. It'll take you through type traits. It'll take you through R value versus L value and a lot of other things. In this episode here, we will start with a crash course on template metaprogramming, or actually just templates in general. Do not run away if you think that it starts out too slow, because it will, but at the end, we will see template argument. That is rather complex. So we start out with the min method. Every tutorial on templates start with min. So who am I to break tradition? Min takes 2 integer and return another integer. And it does it via this very complex algorithm down here. But the key thing is that it takes 2 integer. What would happen if I wanted to take 2 doubles? Or if I wanted to take 2 instances of a foo class? Well, I would have to replicate, and likely, I could use overloading so that I could still call them min, but I could also use templates. And that's where we'll go next. So go to our min here and template min method. This time, lots and lots more code, but do not fear, it's not that bad. Let's hide lots of it. There we are. My min method now, I call it my min this time, and that was a, std has a min, and I'm using namespace std, so that gave me quite some weird error messages. So I call it my min. Okay, what we see here is that my min is a template on type name T. That's a terrible habit that many people writing templates do, that they name their templates T and S and V and W and whatnot. It's like calling your iterators it. Nobody would ever do that, right? Okay, anyway, it's a template method now. We can see that because of the keyword template. And in this bracketed list, I name which types are to be abstracted out. It's the type T. And if I select T, you cannot see, I thought you would see that I have a T here and a T there and a T there. And basically what happens is that, or if I give it like I do down here with my int of integers, then T will be an integer and all of these will be integers. If I give it my int with string, then all of these t's will be std strings. Or if I give it with test, that's a class we have up here, then they will all be test. The only requirement is that my class actually implements the operator less than. If we open here, we'll see that I actually do implement operator less than. I also do implement the operator less than of O streams, but that's just so that I can stream out which of these 2 are the minimum. Observe that this my min is now a templarized method. I didn't specify the type, but I could have written like this if I wanted it to be more explicit. And before you go, this is going too fast, you do this all the time. You write std vector less than the type of your vector. And actually, sometimes you didn't even need that type of your vector if you want. But I can do that. My compiler will deduce that the parameters here are both integers, so T must be an integer. Templates are, of course, useful not just for freestanding methods like min, but also for classes where part of the class can be templarized. We'll see an implementation now of a stack. Again, the typical example of the templarized class. The item types in that stack is temporized in the first version. And then the second one will also temporize the actual container used inside it. But I'm getting ahead of myself now. Let's start out with templarizing. And is that even a word? I don't know. The type of the items. So, as every good story, it starts with the keyword template. It tells me that this is a templated class. The thing that is changing between instance and instance is the type T here, telling me that T is a placeholder for the actual type that is used in different places. So we can see using item type equal to T. That's a trick that is used a lot in metaprogramming, that you later on can go and ask an instance, what is the type of your items, by simply referencing this type name here. I have two overloaded push methods, one taking a const L value and the other taking a R value reference. So this is for regular items, and this is for items that are temporaries. They will be moved into my items slightly faster. Slightly faster, and it works also for those that only can be moved, not copied, as we'll see down in the code below, where we have a stack of unique pointers. I have a pop method here that returns the T, and let's not even go into exceptions and everything involved there, because there's lots of presentations out there telling you that pop cannot even return the value because there could be an exception thrown in there. But I don't worry about that in this code here. I have a size that can tell me the size of the stack, and there's a method print stack. Let's get back to that a bit later. And here we can see that the vector is, or the items is a vector of the type T. That's the type that I was given here. Let's see how I use it. I create a stack of integers, and this time it cannot differ because there's nothing in here that it could come to any conclusion on what type it would be. So I need to specify the type myself. And now I have a stack of integers. I can push 1, 2, and I can push an L value here, and I can print the stack if I so desire. I can also create a stack of strings, and I can do stuff with that. I can create a stack of foos, and I can even create a unique pointer stack. And a unique pointer, that's this unique pointer stack here, is a stack of unique pointers to T. So this is a stack of where the items on that stack is unique pointers of foos. Let's see the print stack up here. The print stack, did I tell you about using for loops in the previous episode? Well, it could have been an algorithm, but it's just a simple for loop printing stack, open square bracket, printing out the items one after the other using cout, and then close bracket there again. Now, if we look at our foo though, we'll see that foo is a super simple struct, just taking an x and a y and remembering those. So how about printing that with the print stack? Because there is no cout that understand a foo instance. Nevertheless, well, you have to trust me on that one. Well, there we are, building. See, it built. Nevertheless, and I can even run it if you want to, this is episode 1 template stack. Episode 1 template stack, that's the one we have here. I can print out the stack. We saw 1, 2, and 3. But how can this even work when there's code that can't compile? Well, see, the key thing to understand about templates is that if you do not use something, then the compiler will not even bother trying to make sense of that. So I don't use the print stack for my foo stack. If I had done that, I have my foo stack here, which is a stack of foos. If I tried to print it, on the other hand, whoom, there's your error message saying, sorry, and let's try and compile and see what the error message really is. And this is where it's actually easier to go and look at the real compile output. Lots and lots of stuff here. It is at the very top complaining. that, hey, I am sorry, but you are trying to take the O stream here and you are giving it a foo. And on this line here, cout less than item. And that actually comes up from this line that we have right here. We're trying to print out. But given that, up until this point at least, I wasn't using my foo stack to call that particular method, it was just fine. So that's a very important lesson about templates. We saw now a template where the parameter was a type, but it can actually also be values. And the example I'm going to show you is a stack of n items, where n is the maximum number of items and it's built into the type that this is a stack of 10 items versus the other stack over there of the same type of items but 15 items. These are two complete different types, and let's see the code for this. Oh no! Turn down all that color. It's blinding me. Why do we? What? Now? Okay, so I am actually the HR director in KDAP, believe me or not. And this all template stuff is just because I'm a very curious person. But if you are a real developer out there that works on real projects, knowing this stuff is not optional anymore. It's 2022, at least at the time of this recording. So maybe you should upgrade your knowledge. Watching videos on YouTube might be a good idea, but you might also want somebody that can guide you and help you whenever you're stuck. And for exactly that purpose, in KDAP, we do have trainings. So we have some really, really awesome trainings on C++, modern C++. Might be worthwhile for you to check out. There's a link right here. And let's get back to that colorless Jesper. So this time, template type name T as before, and then size T, that's this variable type that could be an integer. So just think integer if size T confuses you. Int max size, so that's the size. And if I just do like this, you can see all the places. Well, can't I? No, I will do like this, and then you can see all the places where I use it. So I have an assert now that my size isn't larger than max size. And I use as storage now an array of T, max size. And of course I could have used a vector and reserved max size items. That's besides the point. But the key thing is that it's part of the type now. And if I had an urge to go from a 15 to a 10, I couldn't just do the operator equal to, because they are two different types. Just like string and foo are two different types, I can of course have operator operators, that assignment operator that takes one and convert to the other if I want to, but that's going a bit too far. All you need to know, however, is how I instantiated stack int 5. Now I have a stack of 5 items. If I try to push more than these, I will get an assertion at runtime that, hey, now there's too many items on the stack. The next facility I'm going to show you of template programming is default type parameters. So just like in regular programming, you have a default parameter to a function, you can also have templates parameters that are defaulted. And in our example, it is the container type inside of my stack that could be something else than a std vector, but the default should be a std vector. Template type name item type. So now I got away from the T's. It's item type now, and type name container. It's much easier to read. Hey, it's the item type and it's a container rather than T and S. So stop doing that. The container is defaulted to a std vector of, and you can see I can even refer to the item type down here. So it's a container of item types, and that is just perfect. I have container here instead, and everything else being the same. There is, however, one problem. See, I have an item type here and a container of that item type, the default, but what if I wanted to have so I can now write stack int and stack deque of int. That's perfectly fine, that's the intention. But how about if I wrote stuff like this? I want a stack of integers. So my T, well, my item type throughout is, I will pop off integers here, but my container down here is a deque of strings. So whenever I do a push, what will happen? Well, I'll try and do a pushback of that t, which is, I know is an integer because it's an integer here, onto a deque of strings. And that's what we will see. What? Nope, no errors. I am kidding you. Of course, I know why there's no errors, because I did not use it yet. I didn't use push yet. So we didn't get in that error situation. But now, bam, you are trying to, and let's just build again and see what it was telling us in the compile output here. Oh, wasn't that bad this time. Items pushback t. There are no matching function for call pushback with this here. And the things that will tell me a bit further down here is what the different types are. So that is a bad idea. What I wanted to do was that I wanted to be able to tell it that it should be a deque instead of a vector. Can I do that? Yes, I can. So we've seen a template type parameter, that was our t, or item type. We've seen a non-type template parameter, that was our int size or size t size. And now we'll see a template parameter. That's what the standard call it. And there's a link below to a page that tells you much more about the parameter list to templates. Let me warn you, yeah, down here in the corner, it's getting really ugly syntax-wise, but it is okay. You can handle it. I know it. Let's look. Template, that's good. Type name, item type, so far so good. But now I need to tell it that it's not the full template type, but it's only part of it. And that I do with specifying template again and type name ... I'll get back to what those 3 dots mean. And then class container equal to stud vector. So the equal to stud vector, that part is easy enough. The class container, that's the name of that type here. We're doing well. Why does it say class here? Well, I think it was C++ 17 that they finally allowed me to write type name here instead of class. Actually, I could have written class here and class there and so on. That's an old, so way back then, it was only class, and they realized type name might be a better word for it. Then they introduced, and the two lived together, except in this one place where it, until C++ 17, I think it was required to be called class still. So what I'm saying here is that I have a parameter which is a template on these parameters itself. And it's basically on the items, comma, type name on the allocator. I can't spell the allocator. Alloc. Let's just call it alloc, right? And you can actually see, because that part have bitten me many times, that I just said, okay, let's just do it like type name item here. But then it doesn't work, because my vector is actually, if I go and look at it here, they can't spell allocator either. Okay, allocator. There we are. That is actually a template on 2 things. It's a template on the type and on an optional parameter here, the allocator. So that's what I need to specify over here. It's an item and it's a type name allocator, and I need to go over here again and see what is the allocator. It's a stud allocator of, oh well, what I can do instead is that I can say it's a template. It's a variatic template, so a template of a number of items here, and that's all I need to know. So it's taking an item type and it's taking a template type of container, which is itself a template that can take additional parameters. And the parameters, it's a variatic one. Now we can use it down here. I have a stack of integers, and I have a stack of integers, and deque is the container type in there. That was it for this first episode of a mini series on template metaprogramming. We just got a fast tour over some of the facilities we'll be using, and let me just show you the code again here. This is our end goal, and in next episode we'll talk about something called template specialization, which is a mechanism we also will need to learn about for this code. But just a highlight what we did. We saw a min function that became a template. We saw a class that was templarized. It could even be templarized on a value that was max size. It could be templarized on the container type, and we even had this template parameter where I could just specify the DQ rather than it was a DQ of integers. Until next time, have a great time.